everyone. So today we're going to be talking about gravitation near and within the Earth's surface. Now, before I start this lecture, I am going to say that this is not the most important thing for your AP test. I highly doubt they're even going to test you on this, but you might see, a multiple choice question about this kind of stuff. I doubt that they would do any type of, free response calculation type question with this. But just in case, we want to talk about it and kind of talk about what happens to the acceleration of gravity because our Earth isn't perfectly round and it isn't perfectly, the density is not perfectly distributed. So what exactly happens to the acceleration of gravity because of that? And then what would happen if we went inside the Earth? So this is just some interesting stuff to talk about, interesting stuff to know, just in case they do, ask you any questions about it on the AP test. So let's first talk about gravitation near the Earth's surface. So if we set our universal gravitation equation equal to Newton's second law, which is force is equal to mass times acceleration, we get an equation for gravitational acceleration, which is A sub g in this case. So we know from Newton's universal law of gravitation, we get force is equal to gmm over r squared. Here, that big G is our gravitational constant. Big M is the mass of the Earth. Little m is the mass of anything, any object that we're talking about on the Earth. And then our r term is the distance from the center of the Earth to our object. And then from Newton's second law, we know that force is equal to mass times acceleration. When we're talking about the force of gravity, this is mass times acceleration of gravity. So setting these two things equal to each other, that little m cancels out, and we end up getting gravitational acceleration A sub g is equal to big G times the mass of the Earth divided by r squared. Now, up until this point, we have assumed that free fall acceleration, which is our little g of a particle, is the same as the particle's gravitational acceleration. However, any free fall acceleration value that's measured at a given location will actually differ from the gravitational acceleration value calculated for that location for three reasons. So our first reason is that Earth's mass is not uniformly distributed. The density of the Earth varies radially. The density of the crust varies from region to region over the Earth's surface, and therefore our free fall acceleration little g is going to vary from region to region. So the density of the Earth, it's the densest in the center, and then as the radius increases, the density gets lower and lower and lower. And then, like I said before, the density of the crust is going to vary from region to region. So because of that, our little g, our free fall acceleration, is going to vary from region to region. The second reason is that the Earth is not a perfect sphere. It's actually an ellipsoid, and it's flattened at the poles and it's bulging at the equator. The equatorial radius of the Earth is actually 21 kilometers greater than the polar radius. So free fall acceleration g is going to increase if you were to measure it while moving at sea level from the equator toward the North or South Pole. And the reason for this is because our r term is decreasing when we move from the equator toward the North or South Pole. And then last but not least, the third reason is that the Earth is rotating. So objects on the Earth, except for at the poles, of course, rotate in a circle about the rotation axis and thus must have a centripetal acceleration directed toward the center of the circle. If we draw a free body diagram on, say, this crate that's on the top right here, and then we write a Newton's second law equation for that, we can get this right here, where normal force is the force upwards on the crate from that ground, the surface of the Earth, and then minus the force of gravity, which is directed towards the center of the Earth. And that's going to equal the net force on the object, which is the centripetal force. In this case, we're setting that equal to centripetal force, which is mass times centripetal acceleration. Now, in this case right here, we used omega squared r for centripetal acceleration instead of v squared over r. It is the same thing. We're talking about the radial centripetal acceleration, so you can use either one. And the reason that it's negative is because it's directed also downward on that crate, because our force of gravity is negative as well. It's a negative direction. So here, what we end up getting is mg, which is our apparent weight or our normal force, is equal to m sub ag minus that centripetal force, m times omega squared r. And so that mg that everything is equal to, that's our measured weight. That's our apparent weight or the normal force. That's equal to the magnitude of the gravitational force minus the mass times centripetal acceleration. So if we divide everything by mass here, we get little g, which is our measured acceleration of gravity or our free fall gravitation, equals our acceleration of gravity minus omega squared r. So we get free fall acceleration equals gravitational acceleration minus centripetal acceleration. So there is a difference here. Now this difference is the greatest at the equator because r is the greatest there. But even there, we can find that g is only less than our gravitational acceleration, only by about 0.034 meters per second squared. So this isn't a huge difference, but it is a difference. Now let's switch gears a little bit, talk about the gravitation inside the Earth. So before we do that, we have to talk about this theorem from Newton called Newton's shell theorem. Now what this theorem says is that it says a spherical mass can be thought of as built of many infinitely thin spherical shells, each one nested inside the other. It's for this reason that we can assume that all of the mass on the Earth is located at its center in our calculations. Now, this theorem can be applied to a situation in which a particle is located inside a uniform shell to show the following. A uniform shell of matter exerts no net gravitational force on a particle located inside it. So the reason for this is that the sum of the force vectors on the particle from all the elements is 0. It's not that gravitational forces are just magically disappearing. And we can really see it from this picture right here. If we're measuring the gravitational force on this little m that's inside this shell, we measure it from the left-hand side and from the right-hand side. So we're kind of taking the shell as pieces. Now we can see that little m is farther away from the left-hand side, but as we kind of go out and measure that amount of mass on the left-hand side that is creating that force of gravity on that little m, it is a larger amount of mass, but we're farther away. So because of that, that force of gravity from the left-hand side is actually going to equal the force of gravity from the amount of shell from the right-hand side too, because even though the amount of mass on the right-hand side is smaller, we're closer. So the R is smaller in that case. So it has to do with that inverse square relationship. And where the mass is located and how those forces balance one another out. So because of Newton's shell theorem, we can say that, okay, all these shells are nested inside one another, and then if we have a little mass m that's inside these shells, the mass from one side of the shell, that force of gravity from that mass is going to cancel out the force of gravity from the other side of the shell. So therefore, that gravitational force, the net gravitational force from the shell, is actually equal to 0, no matter where that little mass is inside that shell. So if Earth's mass is uniformly distributed, the gravitational force acting on a particle would be a maximum at the Earth's surface, and it would decrease as the particle moves outward. And that's when we're moving off of the Earth, outward, outside of the Earth, away from the planet. Now, if instead the particle were to move inward, the gravitational force changes for 2 reasons. Number 1, it tends to increase because the particle is moving closer to the center of the Earth, and therefore our R term is decreasing. And it would tend to decrease because the thickening shell of the material laying outside the particle's radial position would not exert any net force on the particle. And that's due to the information that I had on the last slide. So if we started with this is our force of gravity equation, Newton's universal law of gravitation, gmm over r squared. Now here we're looking at big M being the mass of the inside of the Earth. So that mass of the Earth that is still exerting a gravitational force on that particle. So if we assume that the Earth has a uniform density, we can write the inside mass in terms of the Earth's total mass m and total radius r. So density, which we denote as rho, will be equal to inside mass divided by inside volume, which is equivalent to total mass divided by total volume. Because again, density is mass divided by volume, because we're talking about volumetric density here. And because we're assuming that density is uniform, we can equate these two things to one another. Now here we get this in equation form. So we get density is equal to the mass inside divided by the inside volume, where little r is going to be where that particle is located in relation to the center of the Earth. And this is equal to big M divided by total volume of the Earth, 4/3 pi big R, which is the total radius of the Earth, cubed. So if we solve this equation for the mass of the inside as that particle moves inward towards the center of the Earth, we find this mass of the inside. I just multiplied this right here by rho. So we get 4/3 pi little r cubed times rho. Rho, of course, is also equal to this whole thing here. So plugging this whole thing in for our density term, we end up canceling some stuff out, and we get big M, the total mass of the Earth, divided by big R cubed, which again is the total radius of the Earth, times little r cubed. Now what we can do is we can plug this equation into the equation above. So this right here, we're going to plug in for the inside mass that's right here. And so if we plug that in for our inside mass and rearrange a little bit, we end up getting this equation right here, which is the force of gravity from that inside mass as that particle moves inward towards the center of the Earth is equal to big G, which is a constant, times the mass of the particle, which is also a constant, times the total mass of the Earth, which is a constant, divided by the radius of the Earth cubed. That big R is also a constant. And then this whole thing multiplied by little r. Now, little r is the thing that's changing here, because as we move in toward the center of the Earth, that little r is getting smaller and smaller and smaller. So what this tells us here is that the force magnitude decreases linearly as the capsule approaches the center until it is 0 at the center of the Earth.